Hello everyone and welcome to Calculus 6 Real Analysis. In this section we're going to delve into mathematical series, which is a different term than sequences, okay? Actually a series is a sum of a sequence. That's a really big difference. And there's a wide distinction between a series and a sequence, and we're going to see how they interwork together. All right, let's start with the definition of a series. An infinite series is the sum of the terms of an infinite sequence. So the series is the sum of the terms of an infinite sequence. The sum of a sequence is a series. That's the main difference. When we're talking about the sequence alone, okay, the sequence itself, it would be a term like one term, okay, with a variable n that can go to infinity or to a finite value when we evaluate the limit. But the series itself is the sum of these sequences from 1 to infinity. So as an example, sigma n equal 1 to infinity an is equal to a1 plus a2 plus a3 plus etc. all the way to an. Each an is a term in the series, is one term in the series. The series does not represent an actual sum, but rather the limit of the sequence of partial sums. Okay, so the series does not represent an actual sum, but rather a limit of the sequence of partial sums. So you have a partial sum of sequences, and you're trying to evaluate the limit of these partial sums, okay, of the sequence in terms here, like the sequence of partial sums, the sequence of these terms added together. Okay, partial sums, and by the way, mind you that we are still in the introductory part of infinite series. I forgot to mention that, so just as a quick note, okay, that's the introduction to infinite series. Partial sums. The partial sum Sn of the first n terms is defined by Sn sigma from n equal 1 to n, okay? Because it is a partial sum, meaning that we're not adding the terms all the way to infinity. We're adding the terms from the first one, from the first sequence, all the way to the nth sequence. So let's say n is equal to 5. We're adding 5 sequences together. So Sn is equal to sigma n equal 1 to n of an. The series sigma n equal 1 to infinity an converges when the sequence Sn converges to a finite limit. That's a very important key point. So the series sigma n equal 1 to infinity an converges when the sequence Sn, which needs to be limited, okay, or the partial sum of a specific limited number of terms needs to converge to a finite limit s. That is, limit of Sn as n goes to infinity is equal to sigma n equal 1 to infinity of an equal s. So you have a finite limit value for the series, for the limit of this partial sum of the series. So if the limit does not exist or is infinite, then the series diverges. Explaining the difference between a series and a sequence. Okay, so let's say we have a series which is given by sigma n equal 1 to infinity of an. An, of course, is the sequence, which is equal to n divided by n plus 1. Now, an itself converges to 1 as n approaches infinity. Why? Because if you evaluate the limit, whether through using the Hospital rule or by, like, simply intuitively, you pick the highest power terms, which are n divided by n, because 1 becomes insignificant as n approaches infinity. So limit of an is equal to 1. Or if you want to use the Hospital rule, you simply divide by n both the numerator and the denominator. So you end up with 1 divided by 1 plus 1 over n. As n approaches infinity, 1 divided by n in the denominator becomes 0. So you end up with 1. So the sequence itself converges as n approaches infinity. However, not the series, because the series is a sum of sequences, and that's a major difference. That's a major nuance between the series and the sequence. Why? Because actually, again, the sequence becomes one, or like it converges to one, a finite value. So we can say that the sequence itself converges. However, the series becomes the sum of that sequence for our from n equal 1 up to infinity. So which is, okay, for each term as n approaches infinity, it is equal to 1. So the series itself is equal to 1 plus 1 plus 1 all the way to infinity. So it never ends. In other words, it diverges. That's a major difference between the sequence itself and the series. Convergence versus divergence. This means whether the series approaches a finite number or not. Meaning that as you're summing up terms, as you're adding up, you should end up with a finite number where after which you can no longer add. After which the terms to be added become simply zero. This is what it means. And that's the main difference between a series and a sequence. So the necessary condition for convergence, unlike the convergence for a sequence, if sigma an converges, then necessarily limit of an as n approaches infinity should be equal to 0. Why is that important? Why? Because you need to get to a point where it doesn't matter how many terms you're still adding, these terms should be 0, so that you end up, or you wind up with a finite value for the series. Now, this condition, however, is not sufficient. It doesn't necessarily mean that the series is convergent. So as an example, limit of 1 over n as n approaches infinity is equal to 0. However, sigma an itself here, which is sigma 1 over n, diverges because you keep adding up values. And we're going to see exactly how it works out and how to explain it. So types of series, and we're going to start with geometric series at first. We have different types. A geometric series has the following form. S, or the series, is equal to A plus AR squared plus AR to the power of 3. And you should have noticed the pattern by now. So you can keep going on, plus A times R to the power of 4, etc. So what's happening? Actually, R itself is to the power of n for n going from equal 1, from 1 to infinity. So this can be rewritten as S equal sigma n equal 1 to infinity, A times R to the power of n. For n equals 0, it is A plus, and we're adding up, plus AR squared, etc. Now, A is this argument here, the first term. R is what is called the common ratio, which is being raised to the power of n. The series is infinite if it keeps going indefinitely, and finite if it stops after n terms. So what would be the form of a finite geometric series? It will have the form of A times 1 minus R to the power of n divided by 1 minus R for R different than 1. For R different than 1, and also now, for the series to be finite, there's a very important condition, which is R should be less than 1. Okay, so that when you raise it to the power of n, it won't keep going indefinitely. It won't go to infinity. In other words, so imagine if R is greater than 1. Let's say it is 3. Okay, for each number n, you have 3 to the power of 2 plus 3 to the power of, let's consider A equal 1, plus 3 to the power of 3 plus 3 to the power of 4. This diverges immensely. It keeps going to infinity. So you keep adding up larger and larger terms. It never stops. However, so if R is greater than 1, then the series diverges. However, if we consider r less than 1, for any number less than 1, like 0.3, when you raise it to the power of 2, 3, 4, 5, it actually starts decaying, disintegrating, okay? Because it is a number which is 0 point something, less than 1, okay? So it starts disintegrating until it ends up with 0 eventually. That's why for r less than 1, that would be a finite series. And the sum itself would be equal to a times 1 minus r to the power of n divided by 1 minus r, or quite simply, it will become a divided by 1 minus r. Convergence. If r, an absolute value, is less than 1, the series converges and the sum becomes, so the entire solution, or like the answer for sigma n equal 1 to infinity of a times r to the power of n, which is the form of a geometric series, the series converges and the sum is equal to a divided by 1 minus r. Again, a being the number multiplying the term which is raised to the power of n. So let's say s is equal, actually the series is sigma n equal 1 to infinity of 3 multiplied by 1 divided by 4 to the power of n. 3, which doesn't have a power, which is not raised to the power of n, is actually a. So a equals 3. Then you have 1 divided by 4, or 1/4, is r raised to the power of n. That's why it is r. And if you notice, in such case, 1/4 is less than 1. So this series definitely converges. What would be the value of, or the sum of such series? S is equal to a, which is 3, divided by 1 minus r, or 1 minus 1/4. 1 minus 1 divided by 4. And of course, you factor it out, you reduce it to, to make of it a much simpler form. Now, if r, an absolute value, is greater than or equal to 1, the series diverges. Why? Because actually the sum does not exist. You don't have any longer a limited finite value for the sum. Why? Let's consider r is equal to 1. So 1 to the power of 2, 1 to the power of 3, it's still 1. So it is still equal to 1 indefinitely. It will keep going to 1 all the way to infinity. Okay, now the sequence, not the series, the sequence itself, which is an, converges to 1. But the sum of that sequence, which is sigma from n equal 1 to infinity, would be, let's say it is like 1 to the power of n. Correct? And a is equal 1 also. Okay, what would be that sum? It would be 1 to the power of 1, which is 1 over, plus 1 to the power of 2, plus 1 to the power of 3, plus 1 to the power of 4. It is equal to 1 plus 1 plus 1 all the way to infinity. So it never ends. That's why the series diverges. Although the sequence itself, or the term itself, is finite. The term itself, an, okay, is always forever 1. But the series diverges because you're adding ones indefinitely all the way. Now let's do a practice on geometric series. So determine whether the following series converges or diverges. It is given by sigma from n equal 1 to infinity of 2 divided by 3 to the power of n. Of course, you can pause the video, try edit yourself at first before getting back to the solution. So the main form of this series is given by sigma from n equal 1 to infinity of a times r to the power of n, with a equal 1 and r equal 2/3. So sigma n equal 1 to infinity a r to the power of n, r equal 2 divided by 3, which is less than 1. So the series is convergent. And the sum is equal to s equal a divided by 1 minus r, with a equal 1 and r equal 2 divided by 3. So which is equal to 3 divided by 3 minus 2, which is 3. plus 3 minus 2 is 1. So this is the sum, and it's the typical convergent geometric series. P series. A P series has the following form: sigma from n equal 1 to infinity of 1 divided by n to the power of p. So now p, where p is positive, of course, it's a real number. If p is greater than 1, the series converges. Why? Because you are dividing by an increasing denominator that will eventually end up with the series converging to 0, okay, at some point. Like one of the terms will become 0 and you'll no longer be adding to the series. This is what it means. Now, however, if p is less than or equal to 1, the series diverges. As an example, if n equal 1 and p is equal to 1, then it will be a sum of 1 plus 1 plus 1, etc. Okay? If if p is less than 1, okay, you will be dividing by something to the power of 0.34 something, okay, which means that it will be, the denominator will be decaying, which will increase the numerator. The numerator, actually the entire series, will start diverging. Why? Because when you are dividing by a fraction or something to the power of 10 minus 3, 10 minus 4, okay, this will increase the entire series. So the sum would start adding up values that will be much greater than 1, and you will end up having big numbers, and the series will start diverging immensely. Okay, this is what it means. However, when p is greater than 1, the series converges. Why? Because the number you're dividing by is a large number, so it will decay gradually to 0. Telescoping series. A telescoping series is a special kind of infinite series where many terms cancel out when the series is viewed in its expanded form. This cancellation makes it easy to compute the sum, so it is given by sigma from n equal 1 to infinity, an minus an plus 1 equal a1 minus a2 plus a2 minus a3 plus a3 minus a4. So you notice the middle terms cancel each other. So you will end up with a1 minus limit of an plus 1 as n approaches infinity, and the series converges to 1. Alternating series. An alternating series is a series whose terms alternate in sync between plus and minus signs. It takes the following form: sigma from n equal 1 to infinity of minus 1 to the power of n plus 1 times an, or sigma n equal 1 to infinity minus 1 to the power of n times an. Conditions of convergence. In order to test for convergence, we need to run the Leibniz test, which goes by 3 conditions. First condition, at first an should be greater than or equal to 0. Second condition, the series should be decreasing, monotonically decreasing, if I should say that. So basically, an plus 1 is less than or equal to an, or in other words, the subsequent terms are less than the previous terms. So the terms are decreasing gradually. That's the second condition. Third condition is that the limit of an as n approaches infinity should be equal to 0. Another thing to point at is that in such case, the sequence would be conditionally convergent so far. Now, if it's absolutely convergent, we need to test for sigma n equal 1 to infinity of the absolute value of minus 1 to the power of n an. So if it converges absolutely, or in other words, if the absolute value also converges, then it will absolutely converge. Okay, so then it will no longer converge only conditionally, but also absolutely. Even in its absolute value, it does converge as well. Absolute versus conditional convergence, as we mentioned. So a series sigma an is absolutely convergent if and only if sigma of an, an absolute value, converges as well. It's not only according to Leibniz test that we find convergence, but also the absolute value of an when within the series converges. So it is conditionally convergent. if sigma n converges, but sigma of the absolute value of an diverges. As an example, you have sigma n equal 1 to infinity of minus 1 to the power of n plus 1 divided by n, an absolute value. It would be equal to the absolute value of minus 1 to the power of n. Doesn't matter what n is, it becomes plus 1. So equal to sigma n equal 1 to infinity of 1 divided by n, which diverges. Hence, it is conditionally convergent. Now, remainder estimate. If an alternating series satisfies the test, the Leibniz test, then the error when approximating the sum by the first n terms is Rn is equal to S, the value of the series, minus Sn for the n terms is less than or should be less than or equal to An plus 1. Okay, and sorry for the typo here. Power series, another type of series. So it is an infinite series of the form sigma from n equals 0 to infinity, an times x minus c to the power of n. An, the terms that are real or complex, which are coefficients, by the way, either real or complex coefficients. C is the center of the series, so it's often 0. Okay, if C is 0, then you have sigma n equals 0 to infinity an x to the power of n. And x is the variable. It is changing. Now, for the convergence test, a power series converges only for values of x within a certain distance from the center. Here, I might have cropped the distance by mistake. Okay, so you have within a certain distance from the center C, okay, which is also called the radius of convergence. Okay, now it converges absolutely for x minus c, an absolute value is less than r. So x minus c should be less than the radius of convergence. It diverges for values of x, which are x minus c, okay, greater than r. In other words, when the distance from the center, this is what it means. When the distance from the center goes beyond or like outshoots the radius of convergence, then the series would be divergent. Now, it may converge or diverge at x minus c equal r, so it requires further testing. In other words, we can say that the test in such case would be inconclusive. Now, we will see some of the exercises, I think, for the power series. We will check what we can do with them later. Now, the limit and radius of convergence of a series, respectively, they are defined by the limit, L, is equal to limit as n approaches infinity of the absolute value of an plus 1 divided by an. So let's say you have a term an within the series. In some scenarios, in order to test, like this is called, by the way, the ratio test for convergence. So what we do is we evaluate the limit as n approaches infinity of an plus 1 divided by an in absolute value. In other words, let's say you have a series given by n, okay? So, or n squared. This will give you limit of n plus 1 squared, that would be an plus 1, divided by n squared, okay? And you test the limit based on that. And the test of the limit gives us whether the series is convergent or not. Now, another note is that the radius of convergence is equal to the inverse of the limit, which is 1 over L, or in other words, is equal to the limit as n approaches infinity of the absolute value of an divided by an plus 1. Once you find the radius of convergence, you can test the endpoints, check for convergence at x equals c plus minus r manually. Okay, now, and by the way, here in the ratio test, if the limit is less than 1, then the series converges. If it's equal to 1, the test is inconclusive. And when the limit is greater than 1, then the test or the series is divergent. In other words, only when the limit is less than 1, it means that the subsequent terms are lesser than the previous terms, like it's decaying. The entire sequence or series rather is decaying. So when L is less than 1, we have a convergence. L equal 1, test is inconclusive. We need further test. And when L is greater than 1, it means that the subsequent terms are greater than the previous term, so it is diverging. The entire series is divergent. Taylor-Maclaurin series. The Taylor series of a function fx about a point A is given by, and this is, by the way, another definition for the function itself, is given by sigma from n equals 0 to infinity. In such case, fna, this means the nth derivative of f at point A, divided by n factorial, multiplied by x minus a, okay, which is the point, to the power of n. So fna is the nth derivative of f evaluated at x equal a. So you fill within f, like you replace x with a. N factorial, which is the factorial of n, of course, and the series approximates fx near x equal a. That's the importance of Maclaurin, or Maclaurin. Like Maclaurin is the French version of the name. So Maclaurin series is actually a special case for Taylor series centered at a equals 0. So this is basically Taylor series when a is different than 0. Maclaurin series is the same thing, but for a equals 0, for the center being 0. So fx is equal to sigma n equals 0 to infinity, the nth derivative of f at 0 divided by n factorial times x to the power of n. Convergence test. At first, we will start with ratio test. So L is equal to the limit as n approaches infinity of the absolute value of an plus 1 divided by an. Now, if L is less than 1, it means that the subsequent terms are decaying, are less than the previous terms. So the entire series is decreasing. Hence, the series converges absolutely. If L is greater than 1 or L equal infinity, then the series diverges. It means that the subsequent terms, the next terms, always are greater than the previous terms. So the terms that are coming up, that are adding up, are increasing in value. Third, if L is equal to 1, then the test is inconclusive and we need further testing. Second, root test. It is good when terms involve nth powers, okay? So, as for the ratio test, it's so practical when you have a quotient and not necessarily only then, okay? So, for the root test, when you have an nth power, so it would be often beneficial to get the result that you want. L is equal to the limit as n approaches infinity of the nth root of the absolute value of n, of an. If L is less than 1, the same thing here. It converges absolutely. If L is greater than 1, it diverges. And if L is equal to 1, it would be inconclusive. This also helps to find the radius of convergence, by the way, or in other words, the values for which the series converges. So it is given by R equal 1 over L, which is the inverse of the limit. That would be the radius of convergence. 3. Leibniz test. And this is for alternating series. Now, we've already seen that before, but let's see it again from a different or from a deeper perspective so that we would understand it better. This test is suitable to determine the convergence of alternating series, so which are the series that have alternating plus and minus signs. The form of the series would be sigma from n equal 1 to infinity of minus 1 to the power of n plus 1 bn, or sigma n equal 1 to infinity minus 1 to the power of n times b index n. Leibniz test conditions. Okay, when we have a form like this, so sigma of minus 1 to the power of n bn converges if, first of all, bn should be greater than or equal to 0. Then bn should be monotonically decreasing, so bn plus 1 should be less than or equal to bn for all values of n within the natural number space. And limit of bn as n approaches infinity should be equal to 0. If both are satisfied, actually, if the three conditions are satisfied, the first one has been omitted, which is bn greater than or equal to 0, but which is necessary, clearly, then the series converges. To check for absolute convergence, or if the series converges absolutely, because so far, if it meets Leibniz test criteria, it converges in general, we should test the convergence of sigma of minus 1 to the power of n bn. In this case, it would be the series of bn, okay, because minus 1 becomes plus 1, okay. You might have it in the form of minus 1 to the power of n divided by bn. Actually, no, bn is whatever term multiplied by minus 1 to the power of n, which becomes positive when we are testing for the absolute convergence, okay, because absolute value of minus 1 is plus 1. So if bn itself converges, in such case, the series completely converges, like absolutely. We say that it absolutely converges. Direct comparison test, or DCT. The direct comparison test is used to determine the convergence or divergence of a series with positive terms by comparing it to another known series. And here's how it works. Let's say we have sigma an and sigma bn. They are two series. Sigma an is the one that we are looking for its convergence or divergence. This is the one that is under the test. And sigma bn is a known series. Both of them are with non-negative terms, so i.e. an greater than or equal to 0, bn is greater than or equal to 0 for all values of n within the natural space numbers. Then, if 0 less than or equal to an less than or equal to bn, or in other words, if bn is greater than or equal to an for all n beyond some index, and sigma bn, which means that here, remember, these are the sequences. Now, if the series, okay, so if bn as a sequence is greater than or equal to an, and the series of bn converges, then since an is bounded from above by bn, which converges, hence sigma an also converges. Why? Because an is less than or equal to bn, then the series of, or the sum of an also converges if the sum or the series of bn converges as well. Because bn is greater than dn. It is the upper bound. Great. Now, on the other hand, if 0 is less than or equal to bn, less than or equal to an. So an, in this case, is greater than bn for all values of n beyond some index, and sigma bn, the series, diverges. Since sigma bn diverges and an is greater than bn, hence sigma n also diverges. Limit comparison test, or LCT, in other words. The limit comparison test is a powerful convergence test used when DCT is difficult to apply. Let sigma n and sigma bn be series with positive terms. Again, sigma n is the one that is in question, the one that we want to find out whether it is convergent or divergent, and sigma bn is a known series, well tested, like it is known whether it converges or diverges. Now, if limit, and this is the test, we evaluate the limit of an divided by bn as n approaches infinity equal to L, okay, where L is between 0 and infinity. Then both series either converge or diverge together. So if L is a positive finite number, then both series behave the same way. They grow similarly for large n, okay, if L is a positive number. Now, if L is equal to 0 and sigma bn converges, then sigma an also converges if L is equal to infinity. And sigma bn diverges, hence sigma n also is a divergent theory. Differentiation and integration. One of the most powerful properties of power series is that you can differentiate them and integrate them term by term, just like polynomials, only within the radius of convergence. Differentiation and integration. One of the most powerful properties of power series is that you can differentiate them and integrate them term by term, just like polynomials, only within the radius of convergence, of course. So let f of x be equal to sigma from n equals 0 to infinity an x minus c to the power of n, with the radius of convergence r greater than 0. So it converges for x minus c in absolute value less than r. Term by term differentiation, which is necessary at times in order to find or to check the convergence. So f prime x is equal to sigma n equal 1 to infinity n times x minus c to the power of n minus 1. The new series has the same r for convergence radius. Differentiation is valid inside c minus r interval and c plus r. Also, we can integrate term by term for a power series. So integral fx dx, or should I say fn x dx, is equal to c, which is the constant of integration, plus sigma n equals 0 to infinity an divided by n plus 1 times x minus c to the power of n plus 1. Because as a reminder, if you're integrating x squared, for example, you add the power and then you divide by that added power. So integral of x squared gives us x3, which is x to the power of 2 plus 1, divided by 3, which is also 2 plus 1. So the same way here, you have sigma an x minus c to the power of n becomes, after integration, an divided by n plus 1, or x multiplied by x minus c to the power of n plus 1 divided by n plus 1. Again, the radius converges in the same r, and the series is integrable term by term within c minus r and c plus r interval. Integration test. The integral test helps determine whether an infinite series converges or diverges by comparing it to an improper integral. So let fn is equal to n, an, where fx is positive, it is continuous, and fx is decreasing as well for all values of x greater than or equal to n, where n is some integer. Then sigma n equal n to infinity an and integral from n to infinity fx dx both converge or both diverge. So this is why the integration test works. The series and the integral, they either both converge or both diverge. If the integral converges or diverges, so does the series also follow through. Integration test. So let's check the convergence of sigma from n equal 1 to infinity of 1 over n using the integration test this time. Now, of course, we are already familiar with this series, for which you have the form of 1 divided by n to the power of p, where p happens to be 1. So we already know that it diverges. However, this time we're going to use the integration test in order to prove the same thing. So let f of x be equal to 1 over x, which is, by the way, and here's the three main conditions that need to be satisfied before we can use the integration test, which is positive, because 1 over n is positive for whatever value of n, continuous throughout R, of course, except for n equals 0 or x equal 0. Okay, here x greater than or equal to 1. Instead of n, we simply placed x, and decreasing because limit of 1 over x as x approaches infinity is equal to 0. Just the same thing as if saying limit of 1 over n as n approaches infinity is equal to 0. So let's test it using the integration method. Integral between 1 and infinity of 1 over x dx is equal to the limit of ln t, okay, actually its limit, or it is integral from 1 to t of 1 over x dx, okay, for t approaches infinity. Limit as t approaches infinity, integral from 1 or between 1 and t dt. This is how we convert it to an improper integral. Is equal to limit as t approaches infinity of ln t, because 1 over x dx becomes ln x between t and 1, which is equal to ln t minus ln 1, okay, correct? And we already know that ln1 is equal to 0, so its limit is the limit of ln t as t approaches infinity equal infinity. So it diverges. Pointwise convergence of series. Okay, what is a pointwise convergence? Let's say we have a sequence of functions fn. This fn converges pointwise to f on a set A within R, within a like larger ensemble, if for every x within A, the subset of values limit fn x as n approaches infinity is equal to f of x. This means for each individual point x, the sequence fn x converges to fx. However, the rate of convergence can vary depending on x. Okay, the formal definition is for all x within A, which is a subset like a smaller interval within a larger interval, there exists epsilon greater than 0, a very small infinitesimal number, okay? Or for all epsilon greater than 0, there exists nx within n, such that for all n within nx within the set of numbers, the difference between fnx and fx is very small. So they converge, like they approach each other. So the series at n, for n approaching nx, okay, for n very large, these different sequences within the series approach the value f of x. Okay, for the same x, the series is very close to the actual value of the function at point x. Or in other words, in absolute value, the distance between them is less than epsilon, which is a very small gap between them. And note that nx can depend on x as well. Again, what is pointwise convergence in simple terms? Suppose you have a sequence of functions f1x, f2x, f3x, etc. We say that this sequence converges pointwise to a function fx if for every value of x, the sequence of numbers fnx for that fixed x value converges to f of x. Okay? Just like in the definition of the limit, like it's something intuitively similar, okay, not necessarily the very same thing, but if you remember in the definition of limits, okay, when is a function continuous? It is when the limit of that function when x approaches x0 is equal to f of x0 is equal to the actual value of the function of y equal f of x when x is equal to x0. So the limit is also the actual value of the function at that point. Almost the same thing here. So when the sequence for that fixed x value is equal, close to the actual value of the function at x, this means that fnx is convergent. Okay, it converges to f of x. Now the difference here is you won't necessarily hit the exact value in this case, but rather the gap between the value fnx and f of x will be very small, even less than epsilon. In other words, you're fixing a value of x and watching what happens to the numbers fnx as n approach infinity. If those numbers settle down to a limit for each x very close, then the convergence is pointwise. Example, test the pointwise convergence for the following function. fnx is equal to x divided by n for the subset or the small interval x within 0, 1. Okay. We're going to fix x at 0.5. So f1 0.5, which means for n equal 1, is equal to 0.5, f2 0.5 is equal to 0.25, which is 0.5 divided by 2, f3 equals 0.5 divided by 3, or 0.166. So we notice as n approaches infinity, fn 0.5 approaches 0 or tends to 0. The same pattern follows for every x within 0 and 1, okay? So fnx approaches 0 and thus it converges pointwise on 0.5 and hence also on 0 and 1. The same thing, because it is the same thing that happens for x equal 1, same thing for x equal 0. Now let's talk about uniform convergence of series. What is or what does it mean, uniform convergence? A sequence of functions fn converges uniformly to f on a set A, set of values within R within a larger domain if limit of fnx minus fx as n approaches infinity is equal to 0. Okay, so when the limit of the absolute difference between f and x, the series, and f of x, the value of the function at a specific value of x, or like a domain of x, it should approach 0 as n approach infinity. This means all the functions fn get close to f at the same rate across an entire domain, not across or not over one particular pointwise value. Okay, it's not bounded. It should hold for an entire subset, for an entire domain. You can find a single n that works for every x within A, in other words. So for all epsilon greater than 0, there exists n within or among the natural numbers such that for all n greater than or equal to n, for all x within A, within a subset, within an interval, okay, the difference between fnx and fx absolutely is less than epsilon. In other words, all the values of the series within that interval of x's, where x is within a subset, all the values of the series approach the function f of x. Okay, so they converge on an entire subset of values or an entire subdomain, so to speak, not only pointwise, not only at a specific point. That's the main difference. In an absolute way, difference between fnx and fx less than epsilon. In simpler terms, suppose you have a sequence of functions f1x, f2x, f3x, etc. We say that fnx converges uniformly to a function f of x if the entire sequence fnx gets close to fx at the same time for all the values of x within the subset within A. So unlike pointwise convergence, where you fix one x and check the convergence for that point, so by testing if fn of x approaches f of x as n approaches infinity, for uniform convergence, it means that all fnx functions get close to f of x uniformly across all x points, not only just one at a time. Let's say epsilon is the error margin or the gap between, the value of f of x and the value of the series, difference between the convergence value and the real value. You can find a large enough number n such that for all values of n greater than or equal to capital N, fnx minus f of x, the distance between the series and the actual function at x, an absolute value, is less than epsilon. Weierstrass M-Test. Let fn be a sequence of functions defined on a set A. Now suppose there exists constants mn greater than or equal to 0, like another sequence, such that the absolute value of fnx is less than or equal to mn for all x within the set A and all n, and the numerical series sigma n equal 1 to infinity of mn happens to converge. Then the function series sigma n equal 1 to infinity of fnx, for which the sequence is less than or equal to mn, converges also uniformly and absolutely on A. Now, why is that? It is due to the fact that Mn in such case acts like an upper boundary for the sequence of for the series sigma n equal 1 to infinity of fnx. So if Mn converges, then fnx also converges, or if sigma Mn converges, then sigma or the sum of fnx also converges. Proof idea. Okay, since sigma Mn converges for any epsilon greater than 0, there exists n, so that for all values of m greater than n greater than equal to n, sigma of k equal n plus 1 to m of mk is less than epsilon. Then for all values of x within subset A, the absolute value of the sum from k equal n plus 1 to m fkx is less than or equal to sigma k equal n plus 1 to m absolute value of fkx less than or equal to sigma mk less than epsilon. Okay, this is how it works. Because the absolute value or the sum of the absolute value of fkx is less than or equal to the sum of mk less than epsilon. So if mk converges, then so does fkx. This shows the tails are uniformly small, and sigma fnx is uniformly Cauchy, like a Cauchy sequence, and thus uniformly convergent. As a reminder for the Cauchy sequence, okay, as n approaches infinity, the terms approach each other. Even before knowing what they actually approach, which is the final limit, they start approaching each other. They start getting close to each other, their values in term of their values. So as they approach each other, okay, they start converging to a specific value. This is what Cauchy means. The same thing here. So fkx approaches like mk, okay? It works like a Cauchy sequence to some extent. So if mk is convergent, so is fkx. Now let's attempt to re-explain the Weierstrass M-Test in simpler terms so that, we can break it down to more simpler elements, and which is important before we can see it play out in a practice example, which is very important because when you see it in a practice example, it becomes much clearer, it becomes more tangible, so to speak. Let's consider the following series of functions sigma from n equal 1 to infinity fnx defined on some domain. If you can find constants mn such that fnx in absolute value is less than or equal to mn for all values of x, and second of all, sigma or sum from n equal 1 to infinity of mn is a convergent series, which is very important, so that mn not only would be greater than fnx in absolute value, but also being a convergent series, this will make definitely sigma fnx a convergent series that converges uniformly. The analogy is if each function fnx is bounded by a number mn, which is another series, and those mn make up a convergent series, hence the original function series follows through and converges uniformly since the upper boundary that controls it converges as well. Example, consider the following function and test if it is convergent. fnx is equal to x to the power of n divided by n squared on interval 0, 1. We notice that fnx decays very quickly because x to the power of n, since x is between 0 and 1. So anything less than 1 would decay very quickly to 0 when raised to the power of n. So let's consider mn is equal to 1 divided by n squared, where you have, in such case, of course, fnx in absolute value is less than or equal to mn. Why? Because the numerator carries a value between 0 and 1 that when you raise to the power of 2, 3, 4, it decays very quickly, it becomes 0. So it annihilates the entire function. Now, according to Weierstrass, if Mn converges, then Fnx converges as well. Mn is given by 1 divided by n squared, and we notice that, again, Fnx is less than or equal to Mn for all values of x. The form is 1 divided by n to the power of p, where p is greater than 1, hence it converges. Since Mn converges and it happens to be the upper bound or boundary of Fnx, then Fnx converges as well. Exchange of limit or limit operations. Limit of a limit or double limit. Suppose we have limit as x approaches a of limit n approaches infinity of Fnx versus limit n approaches infinity of limit x approaches infinity Fnx. Now, these are not necessarily equal unless the convergence is uniform near x equal a, or some continuity smoothness is present. If Fn approaches f uniformly on a neighborhood of a, and each Fn is continuous at a, then limit as n approaches infinity of limit as x approaches a Fnx is equal to limit as x approaches a of limit n approaching infinity Fnx, which is very important. So we can exchange the limits and still end up with the same result. Limit and integral. Let Fn be approaching f on an interval AB. Then, if the convergence is uniform, limit of the integral from a to b as n approaches infinity of Fnx dx is equal to the integral of the limit as n approaches infinity Fnx dx. That's very important as well. Now, the third criteria, which is the limit and derivative, let Fn approach f on an interval, and suppose each Fn is differentiable. Okay, in such case, then if Fn prime approaches g uniformly, and all Fn are differentiable, then f prime of x is equal to the limit as n approaches infinity f prime n of x. Okay, in other words, we can exchange limit and derivative. So limit as n approaches infinity of f prime nx is equal to the limit as n approaches infinity of f nx prime. So the limit of the derivative is equal to the derivative of the limit. Also very useful in finding convergence. Exercise. Determine whether the following series converges or diverges. Sigma from n equal 1 to infinity of 1 divided by n. Of course, you can pause the video and try to jump on it yourself at first before coming back for the solution. Okay, what do we have here? This is a typical P series having the form sigma n equal 1 to infinity of 1 divided by n to the power of p, where p happens to be equal to 1. So this is a divergent P series. And the proof for that is it will keep going on. It will keep going for the sum, okay, and it never approaches a finite value. So you'll keep adding up. It never decays to 0, so to speak. Okay, another one, determine whether the following series converges or diverges. Sigma from n equal 1 to infinity of 1 divided by n squared. Another one, determine whether the following series converges or diverges. Sigma n equal 1 to infinity of 1 divided by n squared. Seems a little bit similar to the previous one. However, in this case, this 1 divided by n to the power of p form exhibits a higher power, p equal 2, which means it's greater than 1. So the denominator keeps increasing. Hence, this entire series decreases so fast and decays like it approaches a finite value. Okay? Hence, since p is greater than 1, so the series converges. Let's check it out. So, form sigma n equal 1 to infinity, 1 divided by n to the power of p, p equal 2 greater than 1. This series is convergent with p greater than 1. It dwindles down to a finite value, in other words. Determine whether the following series converges or diverges. Sigma from n equal 1 to infinity of minus 1 to the power of n divided by n. At first, you kind of notice something. You can pause the video, of course, and try to figure it out. But as we move on, you notice that this is an alternating series. Okay, with minus 1 keeps alternating between a positive and negative value, which is minus 1 plus 1, all the way, and it is divided by n, okay, which is actually, yeah, the denominator. So this can be rewritten as sigma minus 1 to the power of n multiplied by bn, with bn equal 1 over n. And it requires the Leibniz test to be to find out whether it converges or diverges. Let's check if the criteria of Leibniz are met. Okay, so at first, the general form is given by sigma n equal 1 to infinity of minus 1 to the power of n bn, with bn equal 1 divided by n. Okay, 1 over n, which is the component multiplied by minus 1 to the power of n. This is again an alternating harmonic series for which we need to use Leibniz test. Okay, Leibniz test is given by three criteria again. You have checking if Bn is greater than or equal to 0. That's the first one. 1 over n is always greater than or equal to 0 for all the values of n within the natural space among the natural numbers. That's one. Second, testing if the series is decreasing, which means an plus 1 is less than or equal to an. So we need to check if it is monotonically decreasing. Okay, we need to evaluate bn plus 1 minus bn. By the way, instead of an plus 1, like it's a flop here, it is bn plus 1, not an plus 1, which is the same concept, but we are referring to bn, the component multiplying the minus 1 to the power of n, which is the alternating part. Okay, so it's not an, it is bn. And instead of an plus 1, it is bn plus 1. So bn plus 1 minus bn is equal to 1 divided by n plus 1 minus 1 divided by n. Okay, let's solve it as, you place it equal to 0 and you check whether it is positive or negative. So it gives us n minus 1, okay, or n minus n plus 1 within parentheses divided by n times n plus 1 equal n minus n is equal to 0. We are left with minus 1 divided by the denominator, which is always positive, because for all n, the denominator will always remain positive. And this renders the entire comparison, or this renders bn plus 1 minus bn less than 0, which means that the series is indeed decreasing, or rather this sequence here is indeed decreasing. So bn plus 1 minus bn is equal to minus 1 divided by n times n plus 1 less than 0. So the series is strictly monotonically decreasing. Now, the final test is the limit. So limit bn as n approaches infinity is equal to the limit as n approaches infinity of 1 divided by n, which is 1 divided by infinity, or 0. And hence the three conditions are met, then this series converges. But let's test if it absolutely converges, which is a different aspect of convergence. Now, so absolute value of sigma minus 1 to the power of n divided by n is equal to sigma n equal 1 to infinity of 1 divided by n, which we know it diverges. Why? Because p is equal to 1, the power of n in the denominator. Hence, the series converges conditionally, but not absolutely. Determine whether the following series converges or diverges. Sigma n equal 1 to infinity of 1 divided by n times n plus 1. Now, this can be reformatted as the following. Sigma from n equal 1 to infinity of 1 divided by n times n plus 1 equals sigma of n equal 1 to infinity 1 divided by n minus 1 divided by n plus 1. If you multiply n plus 1 here and here you get minus n, you end up with the original series, okay? Which is the same, or another form rather, of 1 divided by n times n plus 1. So let's develop it. It is equal to 1 minus 1 half plus 1 half minus 1 third plus 1 third minus 1 fourth, etc. And you notice that the middle terms cancel each other. So this is a telescopic series apparently. Okay, so this becomes equal to 1. So what remains is 1, which is the first term. All the other terms cancel each other. So this series converges to 1. Now let's try to check the convergence using the ratio test. So limit as n approaches infinity of an plus 1 divided by an, which is equal to the limit as n approaches infinity of 1 divided by n plus 1 multiplied by n plus 2. So we simply swap n, or replace n by n plus 1, divided by 1 over n times n plus 1, which is equal to limit n approaches infinity of n times n plus 1, which is here the denominator would be flipped back to become the numerator, divided by n plus 1 times n plus 2. So this would be equal to n divided by n plus 2 equal 1, okay? Because as you factor it out, okay, here's what happens. N times n plus 1 is n squared plus n, and here you factor out n, okay, according to the L'Hopital rule. So the point is, this becomes equal to 1, okay? Why? Because you take the variable with the highest power, which is n, because 2, as n approaches infinity, doesn't really count. So limit as n approaches infinity of absolute value of n divided by n plus 2 is equal to 1. Hence, the test is inconclusive. So we cannot count on this method to find the convergence. The ratio test did not work. Hence, we're going to try another approach, which is the limit convergence test, or LCT, which works by comparing this sequence, or this series, which is an, with another series, bn. We divide them together, and we test the limit of an divided by bn as n approaches infinity. Okay, so bn should be a known series, okay, which we know whether it converges or diverges, and we see what the value of the limit would become of an divided by bn. So if the limit is equal to 1, for instance, hence if bn converges, then an definitely converges, or if the limit is equal to infinity, if bn diverges, then an diverges as well. So they follow through each other. Now, so an is equal to n divided by n squared plus 1, which is simply the series that we have, and bn is equal to 1 over n, since 1 over n is a well-known series. Okay, let's evaluate the limit of an divided by bn. So limit of an divided by bn as n approaches infinity is equal to the limit of n divided by n squared plus 1 divided by 1 over n, which is multiplied by n. Okay, we flip the fraction, the quotient, so it is equal to the limit as n approaches infinity of n squared divided by n squared plus 1 equal 1, according to the L'Hopital rule, which is done by dividing both the numerator and the denominator by the highest quotient. Oh, I'm sorry, by the variable with the highest power. Okay, which means that since you have n squared, it is the one with the highest power. So if we divide by n squared both the numerator and the denominator, you end up with 1 divided by 1 plus 1 over n squared. 1 over n squared as n approaches infinity becomes 0, so the limit is 1. Okay, since the limit is 1, if sigma bn converges, then sigma n also converges. If sigma bn diverges, then also does sigma an. Since bn, which is equal to 1 over n, remember the form is 1 over n to the power of p, it diverges because p is equal to 1, hence an also diverges, okay, and this is the solution. So sigma an is divergent. Okay, determine whether the following series converges or diverges, which is sigma from 1 to infinity of 1 divided by n multiplied by ln squared. Okay, again, you can pause the video and try to solve it first before getting into the solution. Form here is 1 divided by n times ln to the power of p, and p greater than 1 because it is equal to. Now, I understand that it's not exactly the form of 1 divided by n to the power of p, but we need to understand that ln to the power of p also increases, okay? It is divergent. Why? Because you have ln, despite the fact that it doesn't increase as fast as n, but remember it is multiplied with n still, it has a power greater than 1, okay, which makes it increase almost exponentially. So the series is convergent because you are dividing by such that great number. It is almost the same form of 1 divided by n to the power of p. Determine whether the following series converges or diverges, which is given by sigma n equal to infinity of 1 divided by n ln n. And of course, it needs to start with n equal to, otherwise, with n equal 1, ln 1 is equal to 0, so the series blows up even before it gets started. Let's try the integral test. Now, you would ask why we can actually use the integration test, because the integration test requires three criteria, three conditions to be met. The first one is that 1 divided by n ln n, which is an, if you want, should be greater than or equal to 0. And it actually is, because for whatever n value you have, 1 divided by n times ln n is always greater than or equal to 0. No negative terms here. That's first. Second, it should be monotonically decreasing. And as you notice, 1 divided by n ln n, the limit for that as n approaches infinity would become 0. Why? Because ln blows up to infinity and it is also multiplied by n in the denominator, so it reaches 0. Okay? That's the second criteria. As for the third criteria, is this series needs to be continuous, and it actually is. It is continuous throughout R. So we can try the integration test to evaluate the divergence or convergence, okay, whether it is convergent or not. X is equal to 1 divided by x ln x. So we simply replace n by x, and we need to integrate from 2 n equal to up to infinity. These have become now the bounds of the integral, okay? So now, in order to solve such integral, we need to evaluate, or actually we need to make a variable substitution, okay? Change of variables. So we consider u equal ln x, and hence the u would be 1 over x dx. Now notice, this is 1 over x multiplied by dx, so this is du, and you have u in the denominator. Of course, also the bounds would change, because for x equal to, then u becomes ln2. As for infinity, ln infinity is infinity, so this doesn't change. So it becomes integral from ln2 up to infinity of du over u, which is ln u between infinity and ln2 equal infinity. So as a conclusion, the series diverges since the integral itself diverges. Determine whether the following series converges or diverges, given by sigma or sum from n equal 1 to infinity of 1 divided by n squared plus 5. Again, pause the video right now if you want to try to solve it before seeing the actual solution. Okay, now how can we approach this problem? Okay, I'm thinking right now one of the best approaches would be a DCT or direct comparison test. What do I mean by that? If you remember, when we have an such as this series here, okay, actually an would be the sequence, would be 1 divided by n squared plus 5. If we can compare it with another sequence like 1 divided by n squared, and in such case 1 divided by n squared n squared would be bigger than 1 divided by n squared plus 5. So if an is equal to 1 divided by n squared plus 5, bn is equal to 1 divided by n squared, bn would be bigger than an. If bn converges, which it does, by the way, then an converges. Why? Because 1 divided by n squared, as you remember, p is equal to 2, 2 greater than 1, so it converges. Hence, an, which is less than bn, since bn has become the boundary, the upper boundary for an, in such case, an actually converges as well. So let us check the solution. So let us try the direct comparison test, DCT. Just as a review, as a reminder, if 0 less than or equal to an, less than equal to bn, or in other words, an is less than or equal to bn for all n beyond some index, and sigma bn converges, then sigma an also converges. Now, if 0 less than equal bn less than equal an, or in other words, if bn is less than an for all n beyond some index, and bn diverges, so what is bigger than a divergent series is definitely a divergent series. Okay? It's so intuitive. So if bn diverges, of course an would diverge because an is greater than or equal to bn. Let's start with an being the original series, which is sigma n equal 1 to infinity, 1 divided by n squared plus 5. We need to compare it with bn, a well-known series. Why? Because it is the closest one to an, which is sigma n equal 1 to infinity, 1 divided by n squared. And we know that 1 divided by n squared is a p series with p equal to greater than 1, which means that bn is convergent. So bn is equal to 1 sigma n equal 1 to infinity, 1 divided by n to the power of p greater than 1. bn is convergent. More than that, we have an is less than bn. Why? Because it is divided by a larger number, which is n squared plus 5 instead of n squared. Since bn is convergent, it works as an upper boundary or upper bound for an. Hence, an also converges. Okay, so sigma n equal 1 to infinity of 1 divided by n squared plus 5 is convergent as well. Determine whether the following series converges or diverges. Sigma n equal 1 to infinity minus 1 to the power of n plus 1 multiplied by 1 divided by square root of n. Okay, now, if you want, you can pause and try to solve it. It is not difficult. Actually, it should have become familiar by now. Okay, let's move on. You can pause it in the meantime, or delve into the solution with us. Okay, what we notice is an alternation of minus and plus signs for 1. Okay, minus 1 is to the power of n plus 1. So it would keep oscillating, jumping back and forth between negative and positive values of 1. Okay, so this is of the form minus 1 to the power of n or n plus 1 multiplied by bn, where bn is 1 divided by square root of n, for which we can launch a Leibniz test. Okay, let's do the Leibniz test. Okay, we need 3 conditions to be met. So, Condition number 1, and as you notice, Bn is equal to 1 divided by square root of n. Bn should be greater than or equal to 0. And as you notice, Bn is actually greater than or equal to 0 for whatever value of n within the natural space numbers. Okay? So 1 divided by square root of n, and we know that the square root is always positive for whatever value of n that you would have. Then for all values of n, Bn is actually greater than or equal to 0. Second condition, Bn plus 1 less than or equal to Bn, or in other words, the series Bn is monotonically decreasing. It is decaying. Okay, so let's check this one. Let's test Bn plus 1 minus Bn to check the monotonicity and like whether it is decreasing or increasing. Bn plus 1 minus Bn is equal to 1 divided by square root of n plus 1, so you simply replace n by n plus 1, minus 1 divided by square root of n equal square root of n minus square root of n plus 1 divided by square root of n plus 1 multiplied by square root of n. Okay, now you notice that, and you already know that square root of n plus 1 is of course greater than square root of n. So this Bn plus 1 minus Bn is always negative, is always less than 0. Hence, Bn is strictly and monotonically decreasing. That's the second test. Okay, third condition is that the limit of Bn as n approaches infinity should be 0. So limit of 1 divided by square root of n as n approaches infinity is equal to 1 divided by square root of infinity equals 0. Hence, the three conditions have been met, and this series converges. Okay, except we don't know yet if it converges conditionally or absolutely. Let's check. Now, for the series to converge absolutely, sigma of the absolute value of minus 1 to the power of n plus 1 times 1 divided by square root of n should be equal, actually, yeah, it should, which is equal to 1 divided by square root of n. This one should converge as well. Now, we notice that we get something that is familiar, 1 divided by square root of n, which is n to the power of 1/2. So p is equal to 1/2. It is less than 1. It should be greater than 1. Okay? So for whatever power less than or equal than 1, the series does not converge. Hence, we can conclude that despite that the three conditions have been met for this alternating series, it is convergent but not absolutely. Okay? Why? Because for p equal 1/2, p is less than 1, hence the series is absolutely divergent and only conditionally convergent. Determine whether the following series converges, the same thing, of course, which is sigma n equal 1 to infinity 5 to the power of n divided by n factorial. Okay, so what can we do with this sequence in order to test the convergence? You can think on it for a moment, take your time, and get back to the solution. Now, since this is a quotient, we can try to test whether it converges or not using the ratio test. Okay, so let's use the ratio test, which is given by limit of the absolute value of an plus 1 divided by an as n approaches infinity is equal to the limit as n approaches infinity of an plus 1 is simply 5 to the power of n plus 1 divided by n plus 1 factorial divided by 5 to the power of n divided by n factorial. Of course, you can flip to multiply this quotient. Okay, so the second hand quotient, the second side quotient, is dividing the first one. In order to fix that, you multiply and then you flip the quotient. Okay, so which is equal to limit as n approaches infinity of. But first, let's break down the first quotient. 5 to the power of n plus 1 is simply 5 times 5 to the power of n, correct? Because when we multiply the same number, we add the power, okay? So this is equated with 5 to the power of n times 5. Now, as for the denominator, remember, for the factorial, when you have 5 factorial, it is 5 times 4 times 3 times 2 times 1. It can be rewritten as 5 times 4 factorial because it is equal to 5 multiplied by 4 factorial, which is 4 times 3 times 2 times 1. So n plus 1 factorial is equal to n plus 1 multiplied by n factorial times n factorial in the numerator divided by 5 to the power of n. So you factor out 5 to the power of n, both in the numerator and the denominator. N factorial also vanishes. So we end up with limit of 5 divided by n plus 1 as n approaches infinity, which is equal to 0, because 5 is divided by a very large infinite number. So since L, the limit, is less than 1 and it's equal to 0, which is much better even. Not much better, but like it is a much better indicator. Hence the series converges. Determine whether the following series converges or diverges. Sigma n equal 1 to infinity n squared divided by 2 to the power of n. Okay. Now, one of the things that I would think of is also the ratio test. I don't know if we can also use the power test. We'll look it over. And in the meantime, you can pause the video to try to solve it first. Okay, so using the ratio test, L equal limit as n approaches infinity of an plus 1 divided by an, an absolute value, which is equal to the limit as n approaches infinity of n square an plus 1, you replace n by n plus 1. So it will become n plus 1 square divided by 2 to the power of n plus 1 over n squared divided by 2 to the power of n, which you need to flip it in order to multiply these two quotients, equal to the limit as n approaches infinity of n squared plus 2n plus 1 divided by 2n multiplied by 2 multiplied by 2 to the power of n divided by n squared. Okay, so now you can factor out 2 to the power of n from both the numerator and the denominator. We end up with n squared plus 2n plus 1 divided by 2n squared. Now, we need to use the Hopital rule and divide both numerator and denominator by the variable with the highest power, which is n squared, okay? Because the highest power that you have is power of 2 for the n variable. So you simply divide both numerator and denominator by n squared, or you multiply them by 1 over n squared, both of them, so that we would not change the equation or the value of it. Okay. So it is the limit of 1 divided by n squared, both multiplying numerator and denominator, is equal to 1 multiplied by n squared plus 2n plus 1 divided by 2n squared equal 1 plus 2 divided by n plus 1 divided by n squared divided by 2. Now 2 over n and 1 over n squared approach 0 as n approach infinity. They decay to 0, so we are left with 1 half, which is the limit. Now 1 half is less than 1, so the series is convergent absolutely, we say. Determine whether the following series converges or diverges. Sigma n equal 1 to infinity minus 1 to the power of n divided by ln of n plus 1. Okay, go ahead and pause the video right away in case you want to solve it yourself at first. Now, what we have here is an alternating harmonic series that keeps swapping or oscillating between minus 1 and plus 1. And it is of the form sigma n equal 1 to infinity of minus 1 to the power of n multiplied by bn. Okay, bn is the part multiplying minus 1 to the power of n, which is 1 divided by ln of n plus 1. In order to test the convergence, we need to use the Leibniz test, which goes under three criteria that need to be met in order for this series to be convergent. One is it needs to be positive, 1 divided by ln n plus 1. Second of all, it needs to be monotonically decreasing. And third, it needs to have a limit approaching 0 as n approaches infinity. So let's start. Okay. It is of the form sigma n equal 1 to infinity of minus 1 to the power of n multiplied by bn, with bn equal 1 divided by ln of n plus 1. Now, ln plus 1, ln of n plus 1 is always greater than or equal to 0, no matter what n would be. Even if n starts from 0, and by the way, n is always positive, ln1 for n equals 0 is 0. So it still meets the criteria of being greater than or equal to 0. And for n positive, as n keeps increasing, the logarithm is always greater than or equal to 0. It's always greater than 0, actually. For n equal to 1 and then increasing from 1 all the way to infinity. Hence, 1 divided by ln of n plus 1 is always greater than or equal to 0. Second criteria, we need to test bn plus 1 if it's less than or equal to bn, which means that the series or this part, which is this sequence, is always monotonically decreasing. So let's solve bn plus 1 minus bn is equal to 0. With bn plus 1 is simply 1 divided by ln of n plus 1 plus 1. Okay? ln n plus 1 plus 1. We simply replace n by n plus 1, which is 1 over ln of n plus 2. So now ln of n plus 2 is greater than ln of n plus 1. Hence, 1 divided by ln of n plus 2 is less than 1 divided by ln of n plus 1, because this is the inverse. Okay? Hence, 1 divided by ln of n plus 2 minus 1 divided by ln of n plus 1 is less than 0. Why? Because this quantity, okay, is less than 1 divided by ln of n plus 1. 1 divided by ln of n plus 1 is greater. So bn is monotonically decreasing. Okay. Now, the third criteria is the limit. So limit of 1 divided by ln of n plus 1 as n approaches infinity equal 1 divided by infinity, which is 0, because ln always keeps increasing to infinity. As a conclusion, the series converges. Now, we still need to check if it converges absolutely. How to test that? Okay, you need to have sigma of the absolute value of minus 1 to the power of n divided by ln of n plus 1 as a convergent series. Okay, now you have sigma n equal 1 to infinity of 1, because minus 1 to the power of n in absolute value becomes plus 1 divided by ln of n plus 1. Let's try to test that using the limit convergence test, or LCT, which is limit of an divided by bn. Okay, we will see which method would work out. Now, if we use the limit convergence test, or LCT, it won't be clear, because limit of an divided by bn, and by the way, if we choose the series 1 sigma 1 over n, okay, an divided by bn and this term divided by this term would give you limit of n divided by ln n plus 1 as n approach infinity. Okay, it's not clear what the limit would be. A better test, or an easier test, let's we start thinking about this one, is using the DCT, or direct convergence test, by comparing an and bn. Okay, now using the DCT, or direct comparison test, we will compare it with sigma 1 over n. Sigma 1 over n, we know that it diverges. Now, 1 over n is less than 1 over ln of n plus 1. Okay? Why? Because of given the fact that ln n plus 1 increases like slowly than n in the denominator. Hence, 1 divided by ln of n plus 1, which is the inverse, is greater than 1 over n. Since we have this fact, okay, now if 1 over n diverges, then what is bigger than that, which is the other sequence, which is 1 divided by ln of n plus 1, also diverges. Okay, remember the DCT or direct comparison test. So the first term decays slower than the second. And since the second diverges, because this is a well-known series, if you remember, it is 1 divided by n to the power of p with p equal 1. So 1 over n strictly diverges. We know that it does. Now, since this one diverges, and what is bigger than this series, which is 1 divided by ln n plus 1, since this is bigger, okay, it definitely diverges. Because remember, you have 0 less than or equal bn less than or equal to an. An is 1 divided by ln n plus 1. bn is less than that, okay? An can be considered as the upper bound for bn. Since bn diverges, then whatever is greater than bn also diverges. Now let's move into pointwise versus uniform convergence. So we have a function fn of x is equal to x divided by 1 plus nx, x varying between 0 and 1 within this small interval or scope. First of all, find the pointwise limit, f of x. Pointwise means find it at a specific point for x equals 0, x equal 1 in the middle, but not throughout the entire interval, okay? Find the limit f of x is equal to limit n approaching infinity fn x. Second question, does fn x converge uniformly on 0, 1? Okay, I've given you time if you want to pause the video. Now let's get started with A. Find the pointwise limit of f of x for x equals 0 at first. So at x equals 0, limit fn x equals 0 or fn 0 as n approaches infinity is equal to the limit n approaching infinity of 0. You simply replace x by 0 divided by 1 plus n times 0, which is equal to 0. Hence, fn x converges pointwise at x equal 0. Let's now test the limit at x greater than 1, which is outside of this scope, by the way. Limit fn x as n approaches infinity is equal to limit of, you have x divided by 1 plus nx, okay? Using the Hopital rule, you divide by x both numerator and denominator. So it is limit as n approaches infinity of 1 divided by 1 over x plus n. We know that as x becomes very large, okay, 1 over x decays to 0. So you end up with 1 divided by n. As n approaches infinity, okay, the entire limit also decays to 0. So for any x greater than 0, the limit is also 0. Now for x equal 1, limit of 1 divided by 1 plus n, you simply replace x by 1 as n approaches infinity is equal to 0. So the series converges pointwise on 0, 1. Now, as a note, for the pointwise convergence, the speed of convergence may vary or be different for different values of x, okay? And how we evaluated the pointwise convergence, we fix the value of x for a specific value, then we take the limit of the function as n approaches infinity. This is how we evaluate the pointwise limit. And for different values of x, you might have different speeds of convergence. As for the uniform convergence, s and x, or the different series, the different functions need to approach the same value of f of x, okay, uniformly, meaning that they need to approach together, okay, with the same speed of convergence. So, for uniform convergence, at first we need to check sup or like the maximum of the difference between f and x minus f of x, which is sup of f n x is x divided by 1 plus nx minus f of x, which is 0 as we evaluated in the previous solution, okay? So sup of absolute value of x divided by 1 plus nx should be approaching 0 as n approaches infinity. As n approaches infinity. Now, let's differentiate to see whether the function is increasing or decreasing. Let's evaluate the derivative. So f prime nx is equal to, and you know how we evaluate derivative. So you have u prime v minus u v prime divided by v squared. Okay? U and v, lest you forgot, are respectively the numerator and the denominator. So u prime v is the derivative of numerator multiplied by v, the denominator, which is 1 times 1 plus nx, minus uv prime minus x multiplied by derivative of the denominator is n here, divided by v squared, which is the denominator elevated to the square power, which is equal to nx minus nx cancels out. So 1 divided by 1 plus nx squared, always greater than 0. So we have this derivative always increasing, and it has the maximum value as x becomes 0. So it keeps increasing. Actually, yeah, its maximum is 1. Now, the derivative demonstrates that the series is increasing with a maximum value of 1. Now, let's check sup f n x minus fx, which is 1 divided by, because we replace x by 1, which is, actually, yeah, we replace x by 1 to check for the maximum of x equal 1, what would be the limit? So fnx minus fx is equal to 1 divided by 1 plus n, okay, for x equal 1. And the limit of this as n approaches infinity is equal to 0. Okay, so they approach, their limit is 0, hence you have a uniform convergence that holds. Okay, they get close together to 0 uniformly. To place it in simpler terms, both uniformly and pointwise, okay, the function needs to approach the same limit, okay, for it to be uniformly convergent. That's the simpler version of the explanation. Checking the uniform convergence at 0, 1. Now, for x getting close to the left of 1, which is 1 minus, f and x would approximately become 1 divided by n. Therefore, the supremum as x varies between 0 and 1 and approaches 1 rather, okay, the supremum of f and x approaches 0 slowly, okay, as n approaches infinity. Why? Because remember, sigma n equal 1 to infinity of 1 divided by n diverges. Because remember, the power of n is equal to 1. It should be greater than 1 for the series to converge. In such case, it diverges. Okay, why? Because sigma n equal 1 to infinity of 1 divided by n diverges because it slowly converges to 0, but not fast enough for the convergence criterion to be uniform. So the convergence is not uniform at 0, 1. Now, since the series does not converge as x approaches 1 at 1 minus, then it is also non-uniformly convergent at x equal 1. Consider the following series. We have sigma f n x n equal 1 to infinity, f n x being equal to sine nx divided by n, for x varying between 0 and pi, or is scoped within the interval 0, pi. At first, test the pointwise convergence at 0, pi, and find the limit, and check, secondly, the uniform convergence at 0, pi. All right. At x equals 0, sine of n times x, which is n times 0, would be 0. Hence, the limit of f and x as n approaches infinity would be 0 divided by n that approaches infinity equals 0. So the series converges at x equals 0. That is the first check for the first point. At x greater than 0, sine and x would keep oscillating okay, or swinging between -1 and +1 as n approaches infinity, okay? So it is limited between -1 and +1. As for n in the denominator would rise to infinity. It would keep increasing. So limit as n approaches infinity of sine nx divided by n would be equal to 0. So it converges for x greater than 0. For x equal pi, the same thing as for x equals 0, because whatever n is equal, n equal 1, 2, 3 sequentially and always greater than 0, this becomes a multiple of pi, which renders the same value for sine n pi equals 0, okay? Sine n pi would always be 0 for whatever n, which leads to the same limit value. Hence, limit as n approaches infinity, not pi here, of sine n pi divided by n is equal to 0 divided by infinity equal 0. So the series converges pointwise. Let's check the uniform convergence at 0 pi. Now, okay, for this function to be uniformly convergent on this interval, we should have limit of sup, I might have forgotten, sup meaning supremum, okay, the maximum value of the difference between fnx minus fx, fnx being the function here, you know, the sequence, minus f of x, which is the maximum value of the limit that we've seen in the pointwise calculations. That difference should approach 0 as n approaches infinity. Now we note that sine nx swings between -1 and +1, so it remains less than or equal to a known series, which is sigma n equal 1 to infinity of 1 divided by n. We will use the Weierstrass M-Test to check if it converges, or Weierstrass, the way you like to pronounce it. So we know that sine nx divided by n is less than or equal to mn, with mn being equal to 1 over n. Why? Because at its maximum, it's equal to 1 over n. Sine nx has a maximum of 1, okay? And other than 1, it oscillates from 1 to -1, okay? As it also passes through the 0 value. So let's check the limit of mn. Limit mn as n approaches infinity, and here we're testing for the sequence, not the series, okay? So that's why there's a nuance, a difference. Okay, we're not talking about the divergence of the series, but the sequence here. Limit of 1 over n as n approaches infinity is equal to 0. Hence, the series converges uniformly throughout the interval 0 pi. Let's attempt to solve this one. F of x is equal to sigma n equals 0 to infinity of x to the power of n. At first, determine the interval of convergence. Find a closed form expression for fx. Verify whether the convergence is pointwise or uniform on the interval -1, 1. Discuss the behavior of the series at x equal 1 and x equal -1. Or I think is not solved here. All right, so you can pause the video and try to solve it at first before going back to the solution. Now the first question. So this is a form of a geometric series, s equals sigma n equal 1 to infinity, a times r to the power of n, where a is 1, r is simply x. Now the criteria of convergence is given by r, an absolute value should be less than 1. Okay, now what would be r an absolute value? It would be x in our case. So x an absolute value is less than 1. Then you have either plus x is less than 1 or minus x is less than 1. Minus x less than 1, you multiply it by minus, so it becomes x is greater than -1. Okay, so you have x is less than 1 or x greater than -1. In other words, x is between -1 and 1 if the series converges absolutely. Okay, so if the series converges absolutely, x should be between -1 and +1. Second question, find a closed form expression for fx. Okay, let's say fx is convergent. What would be the form or the sum for fx, the value? It would be equal to a divided by 1 minus r. In such case, you have a is equal to 1 and r is x, so 1 divided by 1 minus x. Let's check it out. So closed form expression, as long as x in absolute value is less than 1, fx is equal to sigma from n equals 0 to infinity, x to the power of n, equal a divided by 1 minus r, or equal 1 divided by 1 minus x. Verify whether the convergence is pointwise or uniform on the interval minus 1 plus 1. Okay, what would be the proof for that? We need to check for x equal minus 1 and x equal plus 1 whether the series is convergent or not. Let's start with, okay, so you have minus 1 plus 1. Let us denote the partial sum. Sigma n equals 0 to n, x to the power of n is equal to 1 minus x to the power of n plus 1 divided by 1 minus x, okay? Which is, by the way, 1 divided by 1 minus x minus x to the power of n plus 1 divided by 1 minus x. This is where we've gotten that from, okay? Then the remainder error would be fx minus fnx in absolute value is 1 divided by 1 minus x minus 1 minus x to the power of n plus 1 divided by 1 minus x. So it gives us x to the power of n plus 1 divided by 1 minus x. Now fix epsilon to a value greater than 0 for uniform convergence. We want to find n such that for all x between minus 1 and plus 1, you have absolute value of x to the power of n plus 1 divided by 1 minus x is less than epsilon. Just before we move on, and on a quick note, in case you are wondering where we came up with this notation, I need to remind you of the form of the geometric series, which is Sn is equal to a plus ar squared plus etc., which is equal to a multiplied by 1 minus r to the power of n. Here n is considered n plus 1 divided by 1 minus r. This is where this form came from, okay? And n is a natural number, of course, so this is where we've gotten that from. Instead of r, we have x, and a is equal to 1. However, note that the absolute value of xn plus 1 divided by 1 minus x approaches infinity as x approaches 1. Therefore, we cannot bound the remainder uniformly on the entire open interval minus 1 plus 1. Okay, let us now consider a smaller interval minus r between minus 1 and 1, which is half of the interval, where r is between 0 and 1. On this interval, for all x between minus r, we have the absolute value of xn plus 1 is less than or equal to r to the power of n plus 1, and 1 minus x in absolute value is greater than or equal to 1 minus r. Hence, xn plus 1 divided by 1 minus x in absolute value is less than or equal to r to the power of n plus 1 divided by 1 minus r. So, given epsilon is greater than 0, choose n such that r to the power of n plus 1 divided by 1 minus r is less than epsilon. This is possible because r is less than 1, as we noticed. So Rn plus 1 approaches 0 as n approaches infinity. Now, conclusion, the series converges uniformly on any closed subinterval minus r within minus 1, 1, but not uniformly on the whole open interval minus 1 plus 1. Why is that? Because for r equal minus 1, the denominator becomes 2, okay, 1 plus 1. So it no longer converges. That's why this criteria of having a value between 0 and 1, okay, that is positive, is important. Now let's discuss the behavior of the series at x equal 1 and x equal minus 1. At x equal 1, you have sigma for n equals 0 to infinity, 1 to the power of n, which is 1 plus 1 plus 1, all the way to infinity. Okay, hence this sequence, or this series rather, diverges, okay, with constant terms that go all the way to infinity. So it would be equal to n plus 1 approaching infinity. Going all the way to infinity, it approaches no limit value, no finite value. At x equal minus 1, the series becomes sigma from n equals 0 to infinity minus 1 to the power of n equal 1 minus 1 plus 1 minus 1, etc. So like it keeps oscillating between positive and negative values. This is a harmonic sequence that produces plus 1 for n even and minus 1 for n odd. It keeps oscillating, and as a conclusion, it diverges because it's always alternating between plus 1 and minus 1, so it diverges as well. Now let's test the uniform convergence on 0, infinity. So limit of supremum of fnx, which is nx divided by 1 plus n squared x squared, minus f of x, which is the maximum limit, okay, for the maximum pointwise limit that we've gotten, which is 0, okay, it should tend or approach 0. Let's evaluate. So you have sup nx divided by 1 plus n squared x squared should approach 0. So let's evaluate the derivative to see how the function is changing, okay? Because the derivative would give you the curvature of the function if it's increasing or decreasing. So derivative is given by u divided by v prime is equal to u prime v minus uv prime divided by v squared. The annotation of prime means the derivative of u, or like v prime is the derivative of v. U being the numerator and v being the denominator. So the limit gives you, okay, or rather the derivative, u prime v, so it is n times 1 plus n squared x squared minus uv prime minus nx multiplied by 2x n squared divided by v squared. Okay, now we need to solve for 0. So you place the numerator equal to 0. Let's solve it for f prime x equals 0. So n minus n to the power of 3x squared equal to 0. Hence you have, okay, you factor out 1n. So we end up with x squared n squared is equal to 1. Okay. Hence you have x equal 1 divided by n. Okay, now let's replace. So this is the value for which this derivative becomes 0. Okay, this is the value of x for which the derivative becomes leveled out. Let's replace or like reinstate this x value within fn of x to see the solution, right? Okay, to see the point of convergence, which is the leveling out of the function, correct? So we have sought after where the function becomes leveled. It's no longer increasing or decreasing, which is the derivative at 0, correct? When the derivative is 0, the tangent is parallel to the x-axis or y-axis, if you remember in real analysis. Hence, the function is no longer increasing or decreasing, okay? That would be for us the point or like the region of convergence. So for x equal 1 divided by n, let's check what would be or what would become the value of fnx. So f1 over n is equal to n multiplied by 1 over n, which is replacing x by 1 over n, divided by 1 plus n squared multiplied by x squared, which is also 1 divided by n squared. So you factor this out, you have 1 in the numerator and 1 plus 1 in the denominator, because n squared multiplied by 1 divided by n squared is 1, which is equal 1/2. Now you notice 1/2 does not approach 0. So as a conclusion, it is not, this function is not convergent uniformly on 0 infinity. It converges pointwise, however, it does not converge uniformly. Just as a reminder, this was the limit of supremum of nx divided by 1 plus n squared x squared minus 0. Okay, it should approach 0. So, but this did not happen. Okay, so fnx minus fx did not approach 0, but 1/2 instead. So it did not converge uniformly, meaning that the series and the value of the function at that point are a little bit far from each other. The gap is huge between these two. Hence, the function does not converge uniformly over this interval.